numbers the entire screen, so you end up with 10 digits like this one. So this one is, going back, this one is 0.176171875. Did everybody get that? Okay, so then when you look at it, you're like, oh, that's, what do I do? Okay, and so you've got to go back to the measured values. So the measured values for the first number, 0.0045100, how many significant figures? 5. So remember, zeros at the end are significant if there's a decimal place anywhere in the number. Zeros out front, never significant. So I know that this one's got 5 significant figures. What about the other one? It has 3. Zeros out front are never significant. So you always remember that. You may have to keep it in your answer, but it's never significant. So there's 3. So that tells me that I'm going to start from the left. I don't count this 0 because remember, zeros out front aren't significant. So my number, the 1, the 7, and the 6, those are the digits I'm going to keep. The next one is a 1, so what happens? They all round off, right? So anything after the 6 in my answer, so my correct answer would be 0.176. My answer cannot be any more exact than the numbers that are in the measured values of the problem. So then looking at this one, so if I took 1,000,000, which is that 1,000,000 decimal place times 12.56, so this, putting this in the calculator, would just be 1, 2, 5, 6, 1, 2, 3, 4. So that would be what? 12,560,000 is my answer. Everybody got that when they did the math? How many significant figures in that 1,000,000? Oh. How many significant figures in that 1,000,000? There's a decimal place at the end, so it is 7. So there's 7 in this number. What about 12.56? 4. So my answer needs to be rounded to 4. So when you look at your answer, just start from the left. See the first 4 significant figures. The rest are all zeros and there's no decimal place. So what does that mean? They hold their place, so the number doesn't change. Okay, so that answer has 4 significant figures, so my answer would be exactly that. So remember, zeros at the end, it shows how big the number is. I don't drop those zeros off, but my number, that number is no more exact than the numbers in the problem. So when you do multiplication and division, make sure that you do that. Now that's different with addition and subtraction. Addition and subtraction doesn't care about significant figures. So the rule with addition and subtraction is that you want to round to the smallest decimal place all your numbers have in common. So if one of your numbers just goes and ends at the ones place, then everything gets rounded to the ones. If one of the numbers in the addition or subtraction goes to the tenths place, and maybe the other one goes to the thousandth, that doesn't matter. You're going to round to the smallest decimal place that they all have in common. So looking at this one, number 3, first number has 3 decimal places, second number has 2 decimal places, third number has 4 decimal places. So I'm going to round my answer to how many decimals? 2. Because that's the smallest number, that's the smallest decimal place they all have in common. So this one, this 2 decimals. Now don't round before though, just make sure you do the math. So 456.025 plus 2.30 plus 19.2544. And hopefully I did the math right. So 477.5794. Is that what everybody got? Okay. So once you do the math, now you go back and look at that decimal. Okay, I know I got to round to the hundredths place because that is the one decimal place all of them have. It's the smallest decimal place they all have in common. So I've got to find this. It's a 7. The next number's a 9. So what's that going to do? Round it to 8. Okay. So with addition and subtraction, just find the smallest decimal place both of your numbers or all of your numbers have, and that tells you how to round. Same thing if you're doing subtraction. So the second one, 25.896 minus 15.7896. 25.896 minus 15.7896. I come out with, just doing the math, I got 10.1268, no, 64. 64. So now you compare, what's the smallest decimal place they all have in common?
What is that, thousands?
So it'd be tens, hundreds, thousands, the third decimal place. So here's the third, here's the third. So that means I have to count out, here's my third. So what happens to the 4?
It drops.
Just drops off. So my answer would be 10.106. Okay? So now, when you take your exam, and I'm not going to give this to you this week, I will give it to you on Tuesday, okay? When you take your exam, you get a note card. I will give this to you so you can start building your note card. You can put anything you want on one side, okay? Anything. So you can put any of these notes, any of the rules, maybe examples, whatever you're like, as you're going through and looking at chapter 1, you may want to start like making a list. I wouldn't start writing on this like right away. I would start making a list of things that I think I'm going to need help remembering. Okay, so maybe it's a rule, maybe it's a rounding rule, maybe it's a significant figure rule, maybe some examples of significant figures with those blasted zeros in them so that you can remember which zeros are significant and which are not. That type of thing. I have seen students write so small on these note cards that it's almost like I need a magnifying glass to look at. But it looked like they put a lot of information. Remember, you will always have a periodic table. So you do not need to write any periodic table information on here, okay? Because that's like a waste of space. But if you have a really hard time remembering like Fe is iron, maybe you want to put a couple of those ones. If you find difficult symbols and elements and symbols to remember, maybe you want to do that, okay? But I wouldn't start to fill this out until like the weekend before your exam because we've still got stuff we got to cover. So we still have to cover chapter 2 stuff. Okay, so I will give this to you on Tuesday to let you sort of start planning. It is a 4-inch by 6-inch note card. So it's sort of a medium-sized one. It's not huge, but it's not one of the little ones. And you're allowed to write on one side, okay? When you come in to take your exam, you have to show me your note card and flip it over. If there's anything written on the back, you just give it right to me. You don't get to use one at all, okay? Because I've had a lot of students be super sneaky and be like, I'm just going to write on the back too. All right? So when you come in, you're going to have to show me both, one side. So it does require a little bit of planning to figure out what you want to put on this note card. And I will tell you that it really does help you remember stuff. If you spend time like writing really small and writing it out, you actually end up like learning it a little bit more. It helps to keep it in your head. All right, so this last one, 45.01 micrometers is how many kilometers? Do I do this in 1 step or 2? 2. Why? You got to go to meters first. So see, micro is a prefix, kilo is a prefix. So if you see, when you have to do a unit conversion, if you have 2 letters for the unit name, then you know that it's a prefix. If you had just liters or just meters or just grams, then you can do that in 1 step. So this one, because this is a prefix and this is a prefix, you've got to go from micrometers to meters, and meters, you can then go to kilometers. So setting it up, always write down what you have to start with, times in a line. What goes on the bottom? Micrometers. What you start with always goes on the bottom, whether it's 1 step or 2. But since I got to go to meters first, what goes on top? Meters. Whenever you see micro, what goes in front of the term micro? 1 million. Remember not to leave out zeros, right? When you put it in your calculator, count 1, 2, 3, 4, 5, 6 zeros so that you don't end up putting in just 5. Meters gets the 1. Because remember, this is saying it takes 1 million micrometers to make 1 meter. That's step 1. What am I going to put on the bottom in step 2? Meters. The unit that I had on top goes on the bottom. If you were in lab yesterday, you did this a lot. Hopefully that's kind of like starting to get it to cement in your heads. And then the answer that I want is in kilometers. Now kilometers or kilometers, kilometers, kilo is an odd unit because kilo is like the size of a half of a mile. okay, compared to a meter, which is this big. So kilo is the larger unit. And when we talk about these equivalents, the larger unit is the one that always gets a 1. So which of these units gets a 1? Kilo. So if kilo is one of your units, kilo is bigger, it gets the 1. How many meters to make a kilometer? 1,000. So this is the only time when the base unit, whether it's a meter, liter, or gram, the base unit gets the 1,000 compared to deci, centi, milli, and micro. Remember, those are all smaller units. So kilo gets the 1. It takes 1,000 base units to make the kilo. So micro and micro will cancel. Milli or meter and meter will cancel. And so now you know your unit is correct. Your answer is in kilometers. So doing this math, what do?
You divide by 1 million.
Okay, so you put in 45.01, right? So do anything on the top, times 1 changes nothing. So you just put in 45.01, divide it by 1,000,000, and then divide it by 1,000. Everything across the top gets multiplied, and then divide by each thing in the bottom. So this number,
It has got an E in it.
so what does that mean? So yours says what? It says 4.501, and then E what?
To the -8.
Okay. So
Is that scientific? I can't even get the word out.
E, and then a -8. So it says this. Does everybody see that as an answer? You're either going to see this, or you might see 1, 2, 3, 4, 5, 6, 7, 4501. Okay? You're going to see one of those on your calculator. They're exactly the same. Okay? Both of those numbers are exactly the same. What is that E mean? It's telling you it's an exponent. So the E with the number tells you that that means this is 4.501 times 10 to the -8. So they don't write out the times 10 to the, but when you see that E in the calculator, the number after tells you what the exponent would be. Which leads us perfectly into scientific notation. Couldn't have handled that one better, okay? So in that one, 4.501 times 10 to the -8, and that's kilometers. That's the number from the previous slide. That negative exponent, if you see an exponent with that negative number, then you know that this number is smaller than 1. Negative exponent means the number is less than 1. And if I wanted to go back and forth between an exponent and the whole written number, which way would my decimal place need to go? And how many places would it have to go?
That goes to the left.
So if I have 4.501 and I want to change this back to a normal decimal place, it would go to the left. How many places? 8. So I would start here and go 1, 2, 3, 4, 5, 6, 7, 8. So now my decimal is going to be here. I'll put a 0 out front of my decimal because that's the sort of traditional to have a 0 out front. Every one of those little humps that I did, put a 0 in. Okay, so I'm just going to end up adding zeros. And so if you count, those are 7 zeros in front of that 4. So that's a negative exponent. So if you have a number less than 1, you move the decimal place to the right. And the rule is you want to make your number, for scientific notation, you want to make your number between 1 and 9. So that's why the decimal place ends up after the 4, so that I end up with 4.501. So the number, your decimal place in scientific notation always ends up so that you end up with a number between 1 and 9, and the exponents indicates how many decimal places you had to move it. So what if I have a really big number? Where's my decimal place here? If you don't see it, where is it? At the end. Okay, so if you don't see a decimal place, remember it means that the decimal place is at the end. So if I want to take, and if you're going to write this one down, there's 10 zeros. So 1, 2, 1, put 10 zeros. So if I want to change this into scientific notation, which way is my decimal going to go? It's going to go to the left, until I make my number between 1 and 9. So how many places is it going to move? 12. So it'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because I told you there was 10 zeros. But then it's got to go 11, 12. So I know that my exponent is times 10 to the 12th. So by the number of those movements I had to go, that's what that exponent value is telling me. Notice it's a positive exponent because it's bigger than 1. Now, the other thing is you only keep significant figures in that front number. So how many significant figures in that 1, 2, 1 with 10 zeros? 3. The zeros at the end, they're not significant because there's no decimal place. So I would have 1, 2, 1. 1 decimal place, 2, 1. So 1.21 times 10 to the 12th would represent that number in scientific notation. So if you have a calculator, there actually is a way to switch it back and forth. So if you have one of the old calculators. So do you see in number 4 and number 5 on your keyboard? Number 4 and number 5. Number 4 says flow in the green. Number 5 says sci, S-C-I. So if you hit the second button, so if you put in 1, 2, 1, 1, 2, 3, 4, 5, 6. You just put in 6 because you're going to run out of space. So if you just did 1, 2, 1 with 6 zeros, you hit second and psi, and what does it do? So if you have a graphing calculator or a different calculator, you got to figure out how to put yours into scientific notation. And if you're not 100% sure, see me after class and we can make sure that we can do it. Okay? But if you have one of my calculators, do you see that when you hit second in the number 5, it goes to 1.21 and then a little 0.8 up at the top. Okay? That's 1.1 times 10 to the 8th. So when you see those little numbers up kind of like raised, that's telling you what the exponent is. If you have a graphing calculator, you'd probably have 1.21e8.
I'm sorry.
So this is if you put 1, 2, 1 and 6 zeros in your calculator and then switch it to scientific notation, that's what it should look like. Not that number, just because I can't put all those zeros in mine. It doesn't hold it. It doesn't hold 12. Okay? So if you run into challenges, now if you want to go back in the old school calculator, you just hit second and the number 4. So flow, I don't know what flow stands for, but flow puts it back into standard form. So you can actually switch from scientific notation into standard form, second button 4 and 5. Put yourself a note if that's something that you need to remember. If you've got a graphing calculator and you can't figure it out, let me know because I can just show you, I just have to look at it because all of them are different. I like the Texas Instruments. Those Casios drive me insane, but I can still figure it out. Yeah, they're always I don't know. It seems like they're random. Their little function buttons are a little harder for me to figure out. So here's a couple to practice. Okay? So take a minute, put the first 4 in scientific notation, do the last 3, putting them back into expanded form, just to see. Remember that you want to make sure that you only keep significant figures when you go into scientific notation. You may have to add non-significant zeros into a number when you put it into the regular form. Then all those zeros stay. So some of these numbers you'll see don't get much shorter. It does have, if there's a lot of significant figures, it's not that useful. But if there's just a really big or really small numbers, then it really can be helpful. Okay, so how many significant figures in the first one? How many digits did you end up keeping? 6. Okay, so remember there's no decimal place, so those zeros at the end you're not going to keep. But the 0 in between the 2 and the 5 you're going to keep. So here's your significant figures. So I got to keep all those significant figures. So how many places are you going to move the decimal? 9. So it's going to be times 10 to the 9th. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to move my decimal. So I make my number between 1 and 9, but I've got to keep 1.20568. I've got to keep all 5 of those. How about the second number? How many significant figures? 3. So I know I've got to keep those. So that might be the first thing to look at is like, well, how many significant figures? So I've got to keep those 3, but those zeros at the end, no decimal, those are going to disappear. They're not significant. They're just holding the spot. So this, how many places do I move my decimal? So this is times 10 to the 4th. So I'd have 1.25. So those ones, they do kind of make the number a little bit smaller, a little bit easier. Sometimes doing scientific notation doesn't really help. It sort of like makes it even more complicated because how many significant figures in this one? They're all significant. Everybody see that? All of them. There's non-zero numbers at the beginning and at the end, so everything is significant. So I can't drop any zeros or any of these numbers. But if I'm going to put it in scientific notation, decimal place moves how many? Yep, so it would be times 10 to the 2nd. So it's going to 2 places to the left. So it would be 4.56000025 because all those digits are significant. Now this one's a little different than the top ones because this is a number less than 1. So decimal place is going to go which way? To the right. How many significant figures in this number? 5. So everybody got these. Remember the zeros out front, when you go scientific notation, the zeros out front are going to disappear because they're not significant figures, but all the rest of these are going to stay. So this will be 2.5896, and you have to move your decimal place how many? 3. So it's a -3. So if the number's less than 1, when you move your decimal, it'll go to the right, and that's a negative number. So just for practicing. Going down to the bottom one, so 9.5123 times 10 to the 6. Which way is my decimal going to go? To the right. How many places? 6. And so I go 1, 2, 3, 4 to get it to the end. So that means how many zeros do I add? 2, because that would be 5, 6. Okay, you just add zeros to the end. Once you get the decimal place to the end of your number, you just add zeros to make the total number of exponents. So 95123, I'd have to add 2 zeros. What about the last one? 9.52123 times 10 to the -6. How many significant figures? 6. Which way is my decimal place going to go? To the left. By how many places? Okay, so if it goes 1, how many is that going to leave? 5. So I know that in front of the 9, I'm going to have 5 zeros. So I'm going to have 0.12345, then 95223. They're all significant, so I can't drop any of them off. So going back and forth between the two. You have a dynamic study module that is due on Sunday night that is on significant figures, and it does have some exponents. It does have some rounding, some of those types of things to do. So make sure that you go through and practice those. There's really just 2 other things. I mean, we'll talk a little bit about some of the units of measurement, but there's really 2 other math aspects in this chapter to cover. And so one is called percent. So most people understand what percent is when they get a grade, right? So if you got an 80 on a test, that means that you got an 80 out of a possible 100, right? So when they say 80%, this just means 80 right out of that 100, which is the whole or the total. So it's how many you got compared to how many you could have gotten. So percent kind of takes out that fraction or the decimal place by taking whatever the part is divided by the total number possible, or the total collection, the total number of units, and then multiplying that times 100. Because anytime you take how much out of the whole, that just gives you a decimal, right? So if like if you had 10, like in this one, if I had 48 coins, 12 of them are quarters, okay? So if I wanted to know the percent of quarters, how many are quarters? 12. So I have 12 quarters, and how many total coins? 48. So notice if I just did this math, I'd get a decimal place, Okay, take 12 divided by 48, and I just get a decimal place. So what percent does is percent puts it on a scale of 0 to 100. So you take your how many divided by the total possible and multiply that answer times 100. So what is that? 25%. So that's going to say out of 100, 25% of them are quarters. So that's really all that percent is doing, is it's kind of giving you this scale so you can kind of compare, because you like to be able to compare like how you did in comparison to the total percent you could have gotten on an exam. What about the nickels? What would you do to figure out the percent of nickels? Just take 20. That's the number of nickels, so that's the part, divided by the total, which is 48. Whatever you get as an answer, you multiply it times 100, because 20 divided by 48 would be a decimal place. 20 divided by 48 times 100. And you notice that I got 41.66666667. So if you do this on your calculator, what do you have to do with this? Let's apply significant figures in these numbers. So for the first one, 25%, my measured numbers are 48. How many significant figures? 2. 12. How many significant figures? 25%. How many significant figures? 2. So I'm all good with that, right? So this is the right number of significant figures, but you've got to go back and you've got to do the same thing. So in this one, if I had 48 coins, 20 are nickels. So those are counted. So those are exact. This really should have a decimal place here and a decimal place there because they're exact numbers. I counted 20. So it's not like saying, well, I think there's about 20. This one's saying like in the distribution, I have exactly 20. So 20 with a decimal place has how many significant figures? 2. And then 48 has 2 significant figures. So what do I have to do to my percent? Round it to what? So I'd round this to 42. Because that would keep 2 significant figures in my answer. 10 are dimes. So how do I figure that out? So I take 10 divided by 48, just like the previous one. Multiply that answer times 100. And in that one, I would get 20.83333333%. What would you round this to? 21. Okay, 2 significant figures in my measured numbers. So I want 2 significant figures in my percent. So this would be 21%. And then the rest are pennies. So how do I figure out what that percentage is? Okay. Yep, so I could add these ones up. So I could take 20, 30. So I could say, okay, well, I got 42. So that means the pennies are 6. So then 48 minus 42. The difference, the rest of those, if I have 48 coins total and I add up the number of quarters, nickels, and dimes, the rest are pennies. So I can figure out how many pennies there are that way. So by subtraction, that means that I know I've got 6. So then to figure out its percentage, 6 times, or divided by 48 times 100. I get 12.5%. Significant figures with this one. If I was going to round this, what would it be? 6. How many significant figures in 6? There's only 1. So my answer would end up being 10. So I would say there's 10%. Because 6, there's only 1 significant figure in 6. So it depends on your numbers. Those are measured values. So those are numbers that I would have to use. Okay? Now, notice though, when you add that up, add up 25%, 42%, 21%, 10%. If I add up those numbers, 25 plus 42 plus 21 plus 10, what do you get? So if I add up my percentages, they should be 100, right? Because those are all the pennies, quarters, dimes, nickels. Those are all the coins. But what do you get? 98. So did everybody get 98? So sometimes if you round, you can end up changing your answer. So one of the reasons it changed is because I had to round those pennies because I only had 6. So the rule still is you've got to keep the significant figures, but don't round until you get to like your final answers. So if you have to do multiple steps, you don't want to round your numbers until the very end, which is what the question was, what I wanted to know. It didn't say how many coins percent total. It wanted to know the percent of each coin. So those are my final answers, even though they don't actually end up adding up to 100%. So here's one more. So if I have 2 infants that are in PICU, okay, so one infant's weight increases from 126 ounces to 147 ounces. The other infant's weight increases from 86 to 103. So the question is, which infant had the greatest percent weight increase? So if I want to figure out a percent weight increase, what do I need to do with infant 1? Weight increase. How do I know the increase? Subtract. Okay, so I've got to subtract their final weight from their initial weight because they gained weight. So the percent increase, so 147 minus 126. So that is 21 ounces. So baby number 1 gained 21 ounces. Now, if I'm trying to figure out how much of a change, I need to divide this by what? Would I divide it by their starting weight or their final weight? Their starting weight, because that's where they were. They've gained this, so I want to know how much they've gained compared to where they were. So I divide it by 126. Ounces and ounces, percents. Those units will always cancel because both of those units are the same. And multiplying it times 100. So 21 divided by 126 times 100. And I got 16.666667%. So that's my final answer, right? Because the final answer they want to know is percent weight increase. So if I'm going to round this, it would be what? 17. Because 21 has 2 significant figures, so I would round this to 17%. So let's do baby number 2. We started off as a really little thing, only 86 ounces. A wee 5-pounder. So do the same. You take their final weight, 103 ounces, and subtract it from their initial weight, which was 86. And that you got 17 ounces. So if you look, you're like, oh, well, it gained less than the first one did. First one gained 21 ounces. Second one only gained 17 ounces. But I want to know the percent change. And so in that, 17 ounces gets divided by what? By 86 ounces, because it's that starting point. So it's how they were initially to see how much of that increase occurred. Multiply that answer times 100. And what did you get? So it's 19.7674419. That's all of the digits. If I have to round this, I would round this to 20. And to show that there's 2 significant figures, what would I put? Put a decimal. So 20 with the decimal tells me there's 2 significant figures. Just 20 would only be 1. So even though baby 2 is smaller, baby 2 had a greater percent weight change, even though they didn't gain as much. And it's all because they had a smaller starting point. Okay? They were almost 1/3 smaller than the bigger one with that weight gain. So you would say infant 2 actually had the biggest weight increase. So it's not always obvious when you look at them. Like when I first look at those weights, I would think, oh, well, baby 1's got to be bigger because baby 1's bigger anyways. The weights are bigger. But by looking at that percent change, you can see a trend, or you can see more of what happened between the two of them. So sort of baby 2 looks like it's made bigger strides. Baby 2 has put on more weight compared to how small they were to begin with. Okay, so those are percents. Still applying significant figures. Always do rounding though at the end. Don't round numbers as you go along because that can increase any kind of errors that are there. So the last topic. So the last topic that involves some math is density. So somebody had a question about density, so hopefully after this class it'll make sense to you. So remember that we said mass is the amount of substance that something has. Volume is the amount of space that it takes up. And we said matter all have mass and take up space. So all matter has mass and volume. So if all matter has mass, the amount of that mass can vary. So like, you know, you could have like a sheet of aluminum foil, or you could have a roll of aluminum foil. It's all aluminum. So you can have different amounts. You can also have different amounts of aluminum foil all balled up, and it takes up different volume. So we can alter the amount of mass or volume of a sample just by base how much you get out. But if I take the amount of mass a substance has and divide it by its volume, then I actually get a reference number that's going to be consistent. So aluminum is always going to have a certain mass compared to the amount of space that it takes up. And that makes what's called density. So density as a definition is the mass of your sample, typically it's grams, divided by the volume that the sample takes up. Now the volume, if it's a solid, you might have to talk about it in cubic centimeters because solids like have length, width, and height, like a block. So if it's a solid, you might talk about it in cubic centimeters, because you'd have to measure how big it is.
Isn't that the one with the exponent 3 or something?
Say that again?
Isn't that like how the exponent 3?
Yeah, so it'd be cm with a little 3. So a cubic centimeter, you might see it cm with the 3. So that would be a solid, though. If it's a liquid, or if it's a gas, then typically we talk about it in metric. We'll talk about it in liters or milliliters. So this is if we're talking about, so cubic centimeters is common if you're talking about something that's a solid. But if you're talking about a liquid or gas, liquids are oftentimes referred to in milliliters if it's a liquid. And if it's a gas, because gases take up so much space, they don't talk about it in little milliliters, which is tiny. They talk about it in liters. So liters is sort of a larger space because gases take up so much space. So liters is the common volume reference when thinking about something that's a gas. But those are all volume standards. So when they came up with density, they were like, okay, so we need something that's a standard. So the standard for density is water. And it really kind of became like everything else is in comparison to water, because water is so present everywhere. It makes up so much of you on Earth. It is sort of like this fluid that dissolves things, but also helps to maintain and balance heat transfer. So it's involved in so much. Water ended up becoming this standard. So the density of water, 1 gram of water takes up 1 milliliter of space. And so if you weigh out 1 gram, so you put a little cup on the balance, you add drops of water to have exactly 1 gram, then it will take up 1 milliliter of space. Anything that is less dense than water is going to have a density of less than 1. And if it doesn't mix with water, like a piece of wood, it floats. So you know then that wood has to be less dense. But if you take a penny and you put it in water, it drops to the bottom. So you know that its density must be greater than 1 because it's heavier and it doesn't dissolve. Instead, it drops to the bottom. So the density, you can kind of estimate what a density is if you compare it to how it responds to water. And we can do this calculation. So this is one of the sort of first formulas in calculations. You always get 2 out of the 3 numbers. So if you're thinking about density, and we know that density is always going to be mass. And remember I said mass, look for grams divided by volume. If the volume is given, then use that unit. Okay, so like this one, it says a 1.00 liter volume of sugar has a density of 1.29 grams per mil. Determine the mass of the sugar in the sample. So, just like we were doing when we started those word problems that freak everybody out in lab, okay, what do you know? When you read this, which of these 3 things do I know? Do I know density? Do I know mass? Do I know volume? You're going to know 2. 1 is going to be the unknown. So what do I know?
Density.
I know density, okay? So I know that density is 1.29 grams per mil. So that would be like over. Another way of writing that is 1.29 grams over 1 milliliter. So that's the same. So you'll oftentimes see grams per mil, but it's really saying grams is in the nominator, milliliters is in the denominator. So that sometimes throws people when they just see the little slash. It's just a way, it makes it a whole lot easier to write it instead of having to like set it up so it looks like the little fractional formula. But no, that's exactly the same. These are equal. Okay, so you can write it out 1.29 grams over 1 mil or 1.29 grams per mil. Same thing. What else do I know? I know volume. So I also know volume. And I know volume is 1.00 liters. So what do I want to know? Mass. So mass is my unknown. And like I said, you'll always know 2 out of 3. Like when we do gas laws, you'll know 3 out of 4. When we do dilutions, you always know 3 out of 4. So you're basically going to have all the information but 1. And now, if I want to find mass, I have to have mass all by itself in the formula. So see how this formula, and we could simplify the formula and just say D equals M over V. Density equals mass over volume. I got to get mass all by itself. So now you got to think back to like how you do some movement of, by what? Okay, so if I took and multiplied, so I've got to get M all by itself. So that means I have to move volume. Okay, so if I want to rearrange this formula, see in the formula, mass is divided by volume. If I want to solve for mass, mass needs to be by itself. So I multiply both sides times V. And that is going to do what on the right side? What happens when V is in the numerator and the denominator? They will cancel. Okay, so if you have something in the denominator you want to move, multiply both sides by that unit. If you have something that's in the numerator you want to move, then just divide both sides by that unit, and it'll move it to the other side. So now I can say that mass is going to be equal to density times volume. So now I know how to solve it. So I've got to take density times volume. So can I use 1.29 grams divided by 1 milliliter, multiply it times 1.00 liters? So density, 1.29 grams over 1 milliliter times 1.00 liters. Can I do that? Right, so this, see I have milliliters and liters. I can't use those because that's like trying to multiply inches and feet, right? I've got to put them both in inches or put them both in feet in order to be able to multiply to get units to cancel. So this, I'm going to have to convert. And really, you can convert either unit. I like to convert the unit that's all by itself, that doesn't have any other units in it. Just find it a little bit easier. So I need to take 1.00 liters and convert it to what? Milliliters. Well, liters is a base unit, so I can do this in one step. 1.00 liters times in a line. What unit do I put on the bottom? L. What unit do I put on top? ML. When you see milli, what goes in front? 1,000. Liters gets the 1, right? Because milli, it takes 1,000 millis to make a base unit. So instead of being 1.00 liters, this is 1,000 milliliters. Okay, so now I want to plug this in. So I'm going to change my volume. I'm going to still keep the density. Density is exactly the same. But now I'm going to have 1,000 milliliters. And I apologize. You know that that L is supposed to be a capital. I'm really bad about it. Just that's the cursive in me. So now, do you see milliliters and milliliters cancel? So setting it up this way, milliliters and milliliters cancel. That's going to leave me with my answer in grams, which is mass. So this ends up being what? What do I have to do? Just multiply them. 1.29 times 1,000 is 1,290. What's my unit? Grams. It's the only unit that's left, so my unit is in grams. Before you're done, though, go back to the measured units, and you may have to round because, again, significant figures come into play. So 1.00 liters, how many significant figures? 3. There's a decimal place and 2 zeros at the end. That's 3 significant figures. That is a measured number. Now, density is not a measured number. Density is actually like a reference number. So it's kind of like a unit conversion, like when you used like 1,000 to 1. So with density numbers, because it's a known value, I didn't measure density. I actually look it up in a book. Okay, because I know the density of aluminum, the density of gold, the density of sugar. So I would look this up because this is considered a reference number. It is not used in significant figures.
I know this might be a silly question. Was that a one-step correction?
Yes, because liters is a base unit. So I only had to use one step to get from liters to milliliters. Okay, because I know the direct relationship between liters and milliliters, that there's 1,000 milliliters in 1 liter. Whereas remember when we did the microliters to kilometers or micrometers to kilometers, that one, I had to go to the base unit first because there were 2 prefixes. This, liters, is a base unit, so it's just a single step. So now when I look at my answer, if I have 3 significant figures, is my answer okay? Or do I need to round? Is there a decimal? Nope, no decimal, so I'm good. That's 129. The 0 at the end is not significant, so I have 3 significant figures in my answer, so that's good. So whenever you do your calculation, go back to the problem and look at the measured numbers. Density is never a measured number, but it had 3 significant figures anyway, so it wouldn't have really mattered if you had rounded that way. So here's one more. You try this. A tablet of Tylenol weighs 678 milligrams and has a volume of 0.17 milliliters. I want you to determine the density with correct significant figures in grams per milliliter. Write down your formula, write down what you know, what you need to find, make sure that your units are correct, then do the math. So what do I know?
You have D equals 6. Oh, you're asking what do you
So what do I know? And when you read through,
Tylenol weighs 670.
so what's that?
That's the math.
That's mass, right? So I know M. M is 678 milligrams, and it has a volume of 0.17 mils. So that is, what's that unit represent? That is volume. So volume is 0.17 mils. And what do I want to find? D. Okay, now it says I want correct significant figures in grams per mil. So I've got to figure this out in grams per mil. So do I have grams per mil? No. So notice like then, if you're given like a unit value you want your answer in, check your units. So see that mass is not in grams, mass is in milligrams. So that means that I'm going to have to convert this to grams. So 678 milligrams times in a line. What unit goes on the bottom? Milligrams on the bottom, and which unit on top? Grams. Milli gets a 1,000. Grams gets the 1. right? So check the units because you may have to convert one or the other, or sometimes even both, okay? So this one, milligrams and milligrams will cancel. So this is 0.678. 678 divided by 1,000 moves the decimal 3 places over to the left. So now I got grams. Do I have milliliters? Yes. So now my units are right. So now I'm just going to divide them. So density is mass divided by volume. So 0.678 grams divided by 0.17 milliliters. And what do you end up with? 3.988888. Does it keep going eights? Oh.
No. There's only 2 8s. And then
0.678 divided by. See, and I can't like remember this. Okay, 2 8s and then a 2 3. Sorry. 2 3 5 2 9 4. That would be grams per milliliter. Okay, so can I keep all of that? No. So now I've got to go up to my measured values. So 678, how many significant figures? 3. Everybody got that? So I have 3 significant figures in that measurement. How many in 0.17? 2. So that means my answer can only have 2. So remember, in doing the rounding, just start from the left. So my first 2 significant figures from the left is the 3.9. Next number's an 8. So what's that going to do? Round it up to 4. So do I leave it as just 4? I need 2 significant figures. So what do I have to have? 4.0. So if you did that, great. Good job. Okay? Just apply the significant figure rules. Only do it when you get to the end. Nope, decimal place shows you that that 0 is significant. Remember, all zeros at the end, as long as there's a decimal place, then they are significant. Okay? So there's a couple of density problems. I'm trying to think if they're in significant figures or unit conversions. There's a couple of density questions that are in those, but there's also some problems in the post-lecture for Chapter 1. That is due Sunday night, so you can definitely do that. A couple of other things to finish up Chapter 1. We're going to talk about things like density. Density can be applied in medicine to a topic that's called specific gravity. Specific gravity is really just looking at the density of any kind of liquid compared to the density of water. So specific gravity never has a unit because the units cancel. In healthcare, when they talk about specific gravity, they're talking about how dense a liquid is, and one of interest is urine. Because if you are very dehydrated, what will your specific gravity be, high or low? Very high. If you are dehydrated, you have very little water, which means you have a lot of salt and waste in the blood, which gets filtered out into the urine. So very concentrated urine. If you've ever taken care of patients that have urine that looks kind of like brownish in color, kind of amber, almost looks like iodine, you're like, ooh, this person needs some fluid. Okay? And that's all because if there's low water volume, then there's a high waste volume. So specific gravity is a way of looking at the density of water and urine compared to what it should be. So most people, if you drink like normal amounts of water over the course of the day, your urine should be pretty close to the density of water with some waste and some salts. But if you're dehydrated, then you're going to have a much higher waste content, and that's really stressful on the kidneys. So it is a way of kind of evaluating how well is their kidneys working and how much waste are they actually producing. So urinalysis is commonly includes this idea of this density measurement. Temperature. We talked about temperature, and you actually got to measure for the first time using a thermometer in lab. Temperature, when we talk about how hot it is in this room, because right now it's 70. It's 70. It's like 75. And I was like, could you please drop the temperature down to 70 in here? Because when 35 of us get in here, it gets hot, okay? It just gets warm. When there's only 2 people in here, it's not too bad. But when a bunch of people get in, you're emitting all of this heat. So when we talk about it, it's all in Fahrenheit. The United States, we use Fahrenheit. Pretty much the rest of the world uses Celsius, okay? So people come here and they're like, what is this Fahrenheit stuff you speak of? Because nowhere else in the world. Fahrenheit is an environmental scale. So in order to develop the Fahrenheit temperature scale, they monitored like the coldest weather, the coldest day, and the hottest day. And that became their 0 and 100. So like when you think it gets close to freezing it, when it gets close, we don't get like 0-degree temperatures, but like in Norway, in Germany, up in the mountains, they do. It gets like 32 degrees below zero. So that's that. The Fahrenheit is their zero. Their zero was a very cold day. Very cold. Okay? Well below the freezing point of water. So think like up in the mountains. And their 100-degree day was a hot day. But different parts of the world, that's not really the case. And so things don't really stay always between that 0, 100. You know, like we end up with the heat indexes of like 113. We've had actual temperatures above 100 a couple times this summer. It's not been as bad as some summers, but it's still been pretty hot. The rest of the world goes by Celsius. And Celsius, again, goes on water. Water kind of has, in metric, has become kind of like the standard. So like when talking about density, the density of water, 1 gram per mil. When talking about temperature, that's talking about in Celsius, it is the melting point and freezing point of water. So water ends up becoming our scale. So we can see them here. This is Fahrenheit, and here's Celsius. So 0 degrees Celsius, that is the freezing point of water. That became their 0, so that's that standard. 100 degrees Celsius is the boiling point of water. So knowing that, let's do a couple just for comparison. So if 0 degrees Celsius is equal to what in Fahrenheit? 32. So 0 degrees Celsius is equal to 32 degrees Fahrenheit. That's the freezing point of water. This is why you keep your refrigerator somewhere between 34 and 38 degrees. You don't want your food to freeze, but you want it to stay cold enough. So that's where that range is just a couple of degrees above freezing. 100 degrees Celsius, the boiling point of water is equal to what in Fahrenheit? 212. So at 212 degrees Fahrenheit, water boils. So room temperature. So we're going to say room temperature in here. Room temperature is somewhere in the range of about 70, 75. Now in Celsius, that number normally somewhere around 25 degrees Celsius. So that's kind of like an average outside, 25 degrees Celsius. That's kind of like normal room temperature, sort of comfortable day, not too hot, not too cold. So it's your common room temperature. And so if things start dropping, if you're ever in any other country, and they start saying, oh my gosh, it's like 28 degrees outside. What? So anything above 25, think it's starting to get warm. Anything below 25 is getting cooler and cooler. So that's sort of a scale. The only other one I really want you to remember is I want you to remember what 37 degrees Celsius, that's significant. 37 degrees Celsius is body temperature. That is equal to what in Fahrenheit? So 98.6. Well, it helps if you put them in the right spot. 98.6 degrees Fahrenheit. That is normal body temperature. Is everybody's body temperature always at 98.6? No, there is a range. So a lot of times that you'll find kind of like this range with body temperatures. Some people have body temperatures in the 97s. Some people have body temperatures in the 99s, and they're not sick. They don't have a fever. There's just some people are hotter than others. Some of it's dependent on metabolism, but that's body temperature. Those are the 4 number equivalents I want you to learn if you don't already know them. You should know the boiling point, freezing point of water in Celsius and Fahrenheit, regular day or room temperature, Celsius and Fahrenheit, and then also the body temperature in Celsius and Fahrenheit. I do not require that you actually do unit conversions in Fahrenheit and Celsius. Just remember those 4 because those are the ones that you're going to use the most. And those are the ones that it helps if you kind of remember them so you can kind of like judge what a temperature is. The last one is called Kelvin. So we will talk about Kelvin in chapter 7, so we're not going to talk about it for a while. But Kelvin has the same scale that Celsius has, except Kelvin is based on what they call absolute zero. Absolute zero is the coldest possible temperature that a molecule can have. Temperature is really a measure of the vibration of molecules. The warmer molecules are, the more they vibrate. Okay, so the more they vibrate, the more they want to get apart from each other. That causes them to melt, causes them to boil. You're just increasing how fast those molecules are moving. Absolute zero is the temperature at which molecules stop vibrating. So they can't get any colder. If they stop vibrating completely, your temperature can't get any lower. So just as a number, Kelvin, it's zero. Well, and there actually is no degree for Kelvin, which I really don't like, but 0 degree Kelvin is equal to minus 273 degrees Celsius, which really roughly is equal to about minus 456 degrees Fahrenheit, almost 500 degrees below zero in Fahrenheit. Really cold, okay? And we do have freezers, so like scientists do have freezers that actually approach that, but that is very, very cold. They have gotten things that cold, but they don't stay that cold for very long because that requires a lot of energy in order to chill things. But we will talk about Kelvin again. Just make sure that you know those 4 temperature values in Celsius and in Fahrenheit for class. Okay, so remember I said like you have this normal temperature, 98.6, 37 degrees. Anytime the temperature goes above 40 in Celsius, that's above 104. That is considered hyperthermia. Hyper means what? Hyper means high, right? You have a hyperactive kid, very active. Okay, highly active. So when you think of hyper, always think it means above normal, because we're going to talk about like hyperglycemia, hyperthyroidism. So you see the term hyper a lot in medical terms. Hyper, always think it's always above. This can cause irreversible brain damage. So this is why there's a concern if body temperature rises above 104. It can cause convulsions. It can cause a person to go into a coma. It can cause neurons to basically die and they don't grow back. So that is the concern with very high fevers. Body temperatures below 35. So if your core body temperature drops below 95, they call that hypothermia. So hypo means low, right? So I always think hypo and low, they kind of sound alike, the O's in there. Hypo is low, so that is low. We'll talk again, hypoglycemia, hypothyroidism. We'll talk about hypothermia. Anytime you see hypo, remember that that means it's lower than normal or below what it should be in its range. And so this, though, is kind of an interesting one because people have been chilled so that they're below 95. In fact, they've been chilled by falling in like very cold water and drowning. They pull them out of the water, their body temperature's in the 80s, their heart's not beating, they have no brain function, but what can they do? You can resuscitate them. How? You warm them back up, okay? So they have found when you do this, everything slows down. Your heart rate slows down, your respiration slows down, but cell death slows down too. So this is why people have been pulled out of ice, pulled out of like the avalanches and such, where they are not responsive because their body temperatures drop so low. If they carefully warm them up, they can actually stimulate the return of normal heart rate. So it's kind of cool. People have been like clinically dead and then brought back to life with very minimal nervous system damage. And it's all because when you chill things down, like why do you put your food in the refrigerator? So that it doesn't what? Go bad, so it doesn't spoil, so mold doesn't grow in it, so bacteria doesn't grow. Same thing, if you take the body temperature and drop it, then that helps to slow down all of the breakdown processes. That's why, what's the temperature in an operating room? Freezing. If you've ever had a surgery, they like wheel you in and you're like, oh my God. Like feels like the temperature drops like 10 degrees the closer you get. That's also why. Because by cooling it down, that slows microbe growth and it also helps to slow metabolism of that patient so that they stay more stable compared to keeping them up at that 98.6. All right, so that ends this, because like I said, we're not really going to talk about, we talked about energy early on, potential kinetics, so all of this should be pretty much review. This ends chapter 1. Yay. And so we're right on time. This ends chapter 1, so for next Tuesday, make sure that you have pre-lecture 2 finished. I did extend it. I was supposed to be due today. I pushed it back till Tuesday. So in Mastering Chemistry, you should see it on your calendar. For this Sunday, you need to do the post lecture for chapter 1. All this that we've covered, you should be able to answer all of those. So that's a good test. You should also do the significant figures and unit conversions if you haven't already done those dynamic study modules. Pull up Mastering Chemistry, go to the calendar, do everything that's due Sunday. Then you can go ahead and do what's due Tuesday, and you'll be all ready.